Everyone, thanks for tuning in to this week's demo. Today we'll be talking about Harry Potter and word embeddings. The idea here and the motivation is that often with machine learning and deep learning, we're interested in working with text. We want to do some kind of natural language processing. The issue, of course, is that we think of words as letters and different representations on a screen, and our computers think of them as different ways of representing the letters in binary and stringing them all together. But this way of thinking about words is not meaningful to a computer in the same way that pixels in an image are meaningful to a computer. So we need some way of converting a word into a smaller representation of that word, while that representation captures some of the inherent meaning in a word. And that's the big idea. And once we do this, then we can use our words for whatever downstream task that we want. We could do something like next word prediction or classification of the sentiment of text. But before we can do any of these very cool applications, we need to represent our words in a meaningful way. This problem is challenging because the meaning of words is not transitive. For example, the word wizard is similar to both witch in the magical sense and man in the gender sense, but that doesn't mean that witch is similar to man. So there are lots of these examples where some words are similar to each other because they agree in some way. Maybe it's gender or magicness or sound or anything else. But that doesn't mean that these words are similar to each other. So we need some way of capturing the meaning behind words, and that on the surface is quite challenging. Today we'll talk about two approaches to this problem. The first approach is something called word-to-vec. Vec is short for vector here, so it's a way of encoding a word into a vector. Word-to-vec is a quite popular approach that was proposed, I think, in the early 2010s. The key concept is to find words that are similar to each other. We do this by scanning a bunch of text and identifying words that appear next to each other. And if they appear next to each other, we'll suppose that they're similar. Now, once we have two similar words, let's call them X and Y, we're going to feed X through a neural network. This neural network is very simple. It consists of two layers. The first layer maps the dimension, which is the number of words that we have, to a much smaller dimension, n. So we're going from basically a one-hot encoded representation of a word into a much smaller representation of the word, but it's more dense now because each one of the values here isn't 0, 1 anymore. There are lots of complicated numbers that could be involved in the representation of that word. And this is the thing that we want to represent our word. So we go from a vector where the ith dimension corresponds to the ith word, and a word is represented as having 1 here and zeros everywhere else. We go from that very sparse representation to a very dense representation in n dimensions, and this will be the vector that we're using to describe our word. How do we know that this vector captures the meaning of the word? Well, we're going to train this model by adding another layer to it. This layer maps this n-dimensional vector back up into v-dimensional space, which is quite larger. And we apply softmax to it, and we train it so that when we input x through this process and we get some output, we want the output to be close to the similar word that we found, y. In this way, we enforce that the representation of x and y become close to each other. Now, this process is quite popular. It's called word-to-vec, and word-to-vec is very common to hear people discuss it. But unfortunately, there are several issues here. The first issue is that we do all this training. We train two fully connected layers, but when we use the representation, we only use the first layer. If I want to convert a word into a vector, I only use this layer to do that process. The second issue is that the thing we really want is the embedding of the two similar words to be close together. However, this loss function doesn't necessarily cause that to happen because we're using cross entropy here, and it's not necessarily clear that the way that achieves like a good loss is to make these two vectors similar to each other. Okay, because of that, we're going to introduce another approach, which is called contrastive learning. Contrastive learning is more direct. It's a more direct way to get a meaningful vector representation. The key idea is that we have both positive pairs whose vector representations we want to be close, and negative pairs whose vector representations we want to be far apart. So a positive example in our context of embedding words, would be words that appear next to each other in a sentence or paragraph. And negative pairs will be all other words. So if I find a word in one sentence, another word in another sentence far away, I'll say that that's a negative pair. Notice one thing that should come to your mind is that it's possible that a negative pair is actually a positive pair. Perhaps like I have two words, such as cat and dog, and they often appear next to each other, but I also happen, when I'm sampling negative pairs, to get cat and dog when they appear far apart from each other. That we'll say is actually fine because it happens relatively rarely. So we are allowing some negative pairs to be positive, but because we weight them in such a way, this really isn't an issue for us. Okay, so we have positive pairs, so we know we're close together, and we want to make the representations close together, and we have negative pairs. Let F be the network we apply to the words to the embedded. Oh, let me change this slightly here. This should be F of X and F of Y. Because we're really talking about the embedded representations of these words, not just the words themselves. Okay, so let F of X be the embedding of X and F of Y be the embedding of Y. We want the inner product between these two, which is a measure of similarity for vectors, to be close to 1. So one way we can enforce this is to take the difference between the inner product 1 and square it. Now, to achieve a small loss here, we need to make sure that this inner product is indeed close to 1. This is for positive pairs X and Y, which we know are similar. Now let's consider negative pairs X and Z. We want this inner product to just be small between the embeddings of X and the embeddings of Z. We can enforce that by just squaring this value so it's always positive, and then we achieve low loss if this value is small. Notice that there's some inherent weighting here. We need to choose how often that we want to encode the positive loss, sorry about that, positive loss versus the positive pairs loss versus the negative pairs loss. And there are lots of arbitrary decisions that goes into this. This is just one way of creating a loss function for contrastive learning, but generally the idea is the same. But we want positive pairs embeddings to be small and negative pairs positive pairs embeddings to be large and negative pairs embeddings to be quite small. Okay, that's the setup. Today we're going to implement contrastive learning. We do contrastive learning instead of word2vec because it tends to work better, and it's a more direct way of getting the property we want, which is that similar words have similar embeddings. We'll make this a little bit fun by using the text corpus we'll use is all of the Harry Potter books. Okay, so let's begin. Did this run? Let's try running it again. The first thing we're going to do is load all our libraries. Then we're going to load these books. Luckily, people have posted them in text files online. So this is the first book, chapter 1, The Boy Who Lived. We do this for all of them. We'll process them, and then we'll create one giant text file, text. At this point, we're doing a training, so yeah, sorry, that won't run for a bit. But what we see here is it's just the raw text with a little bit of processing to it. The next step of this is to convert the long set of text. Maybe this will run now. Nope. Okay. At some point that'll run. The idea is that here we just have strings of characters. We want to convert those characters into tokens. Tokens can be thought of constituent parts of natural language. We're going to use words as our tokens today, but you could use syllables or even different characters as your token. So let's look at this. This is just lots of text here. Of course, there's some processing that we need to do because we still have backslashes and apostrophes and s's, so we want to be able to remove all those things. And let's process that. The first thing is that we want to convert this so that each one of these words is its own token. We can do that by basically splitting up the text. The first thing we're going to do is process it so we only care about letters. We get rid of all apostrophes and exclamation marks and question marks, etc. So we're only left with lowercase letters. And we do that for each one of the things that we split in this text. Once we do this, we only get the words that appear frequently. So we want them to appear, in this case, at least 50 times. If they appear 50 times, then we say that's frequent enough that we want to learn some embedding for them. After we've done this, we can look at the tokens, and the tokens are these: the Harry Potter and the Boy Who Lived, Mr. and Mrs. Durley of Number 4 Privet Drive, etc. Some of these words are missing because I guess they didn't appear frequently enough in the corpus for them to be used, which is fine for our purposes. Now we can look at this processed version of these tokens. It looks like there are 971,000 different tokens here, and there are 38,000 different unique tokens. So this number is still quite large, but it's much smaller than the total number of tokens that we have. Now we will map each one of these tokens to a unique index. That'll give us a representation of the, like we need some way to represent each word. For now, we're just going to associate with an index from 1 to 38,000. Once we've done this step, we will process the tokens in such a way that we get the X and Y, our positive examples. So our positive examples will consist of, we go through the word, we have a sliding window, which is how close we'll consider words to be if they're a positive pair. So in this case, if a word is next to each other or one word away from it, we consider it a positive example. And then we add it to X and Y. X will consist of the first word and Y will consist of the second word. And then we're going to train it so that the embeddings of X and Y are close to each other. On this line, we do a check to make sure that the frequency of the particular word that we're adding isn't too large. This is to avoid words like the appearing too much time in our data, which could potentially skew our result. Now that we have our data ready, we will put it into a data set. The data set is very simple. This is just a list of indices. We can print it out and check. This is a tensor. The shape of this is quite small, 84, I guess, because that's just this particular batch that we're looking at. And Y is a corresponding tensor of a similar shape, and this just consists of the indices of the other words. We're representing them as indices instead of the one-hot encoding just to save space here. Now that we have this data loader, we will define our model. This should not be word2vec. I'll call this just model, and I'll have to change that down here too. Maybe, yeah, model's good. It's no longer word2vec, which is the reason I just changed it. The only thing we're doing here is embedding. So this is basically like a fully connected layer, except instead of having to multiply matrices to do a fully connected layer, an embedding is just a more efficient way of, for each index, storing the corresponding vector, and then we can update the weights of those vectors during the training process. Now the contrastive loss, this is a little bit clever. X embedded is a matrix of size batch size by embed dimension, and Y is also the same thing. So this consists of this, each one of their batch size rows, and each one of the rows consists of the vector representing that word. Now, in order to compute the similarity between these, we're going to take the dot product of them. One way to do this at once for all of them is to compute what's called this gram matrix. This gram matrix, if you do dimensional analysis, will have dimension batch size by batch size. And the ith jth entry in this matrix will correspond to the inner product between the ith embedding and the jth embedding. Notice that when I is equal to j, when I equals j here, that is corresponding to X and Y values that are actually close together. So it's a positive pair. So we want the on diagonal parts of this matrix to have a large weight. All the off diagonal entries, when I is not equal to j, we want that to have small weight because that's the inner product between words that are not necessarily associated with each other. One way to implement this quickly is to subtract off the identity from this gram matrix, and then we take the square of each entry and normalize by the number of entries in this matrix. The idea here is that we're forcing everything on the diagonal to be close to 1. So if two word embeddings should be similar to each other, we want their inner product to be close to 1. And if two word embeddings are not necessarily similar to each other, they're a negative pair, we want them to be we want their inner product to be small, close to 0. We achieve it with this loss function. Now we can run some trading, we load our model, we choose a simple standard atom optimizer, and we do the training. Amazingly, the loss function starts out quite large, and after it looks like 10 steps, we're able to get very, very small loss, which is excellent for our purposes. It's one thing to see this loss in practice, but let's also take a little bit of a look at what's going on with our embeddings. One way of doing this is to figure out if we embed a particular word, which words is it closest to? So in this case, we're going to embed the word Quidditch. We're going to look up its index using this dictionary word to ID. And then we'll pass this target index through our model, through this embedder. And we'll do the same thing for our candidates. Our candidates in this case is just all of the different indices of our words. And then we get embeddings for all the candidates and our embedding for our particular word target. We'll compute the similarities between them similar to what we did before. So the dimension here is num candidates, really num tokens by embed dimension. And this is just embed dimension. So when we multiply this together, similarities will be a num tokens dimensional object. And we can check that right here. If we look at similarities.shape, it should be the number of tokens we have by 1. And if we look at the largest values here, and we then convert them back from their ID to words, we see that the words that are closest to Quidditch are pitch, Quidditch, final, win, practice, cup, field, excellent match, and game, which are indeed actually close in meaning to the word Quidditch. It happens on a pitch. There are like final Quidditch matches. You win at Quidditch, you practice it. There's a Quidditch cup. You do it on a field, and the game is quite excellent. You are welcome to play around with other words here. It will not work so well for words that are quite common because we limited the frequency of them, but words that are less frequently, then you can find here. So it looks like wizard is close to fully and law, which I don't quite understand, but it's dressed close to wizard, witch, horcrux, Phineas, that's funny, evil, Grindelwald, and Nicholas? I'm not sure that is. I should brush up on my Harry Potter lore. But it's close to witch, which is quite interesting. Which in turn is close to wizard and lots of these other words. So hopefully you're convinced that by training this process, we've trained it from scratch. Notice we haven't done anything with the pre-trained embedder here. We're able to, just by comparing words that are close together and saying that we want them to be similar, we've been able to embed our words in a way that similar words are close to each other. One thing we can do, because our embedding dimension is quite small, I think we set it to 64 somewhere. Yeah, we set the embedding dimension to 64. One thing that we can do is actually plot this, like each one of these words in that space. So here, each one of these lines corresponds to a particular dimension, and the color represents how, let's say blue is positive and red is negative, and if it's a stronger color, it's further away from 0. We can plot them in this way, and then we can look at these words to find ones that are similar to each other. So for example, these are just the different houses in Harry Potter. It looks like there are definitely similarities between them. For example, on this dimension, it looks like they're all different shades of blue. Here it looks like Gryffindor, Hufflepuff, and Ravenclaw are all similar to each other in like these few dimensions. I don't know what's going on with Slytherin there. And then if you look at different people, such as Voldemort, Snape, and Dumbledore, maybe they are all similar on this dimension, which could correspond to something like wizardry or being a person who appears a lot in these books. But there are some other dimensions where only 2 of them agree. So for example, Dumbledore and Snape and Voldemort look like they agree on this dimension. Maybe Snape does as well. Yeah, so of course, the high level idea behind these word embeddings is that we'd really like it to be that each dimension corresponded to something meaningful. So it could be whether it's a house cup or whether it's a wizard, or whether it has to do with magic, or whether it's good versus evil. Of course, we can't actually get the algorithm or the function, the model, to give us exactly those embeddings, but maybe it does something similar. Maybe in having to figure out which words are similar to other ones, it can discover different dimensions, in which case these words are close to each other. So that's all I had for you today on word embeddings. Thank you for your time, and as always, please feel free to reach out with any questions. Thank you.